I'm just going to take 2 minutes to first tell you a little bit about myself. Then we're going to do a thing to see if we can get the juices flowing to see how the rest of the question and answer can go, because I'm primarily here to be at your service and answer questions as much as possible. And I got some in advance, and I can happily answer those.
Can I ask you to use a mic so the people on Zoom can also hear you?
Yeah, I'll do that. So I can walk around with this, or you want me to stand in one place behind the questions? Really? Okay. Guys, I'm going to stand over here. I wanted to walk around and be a little bit more informal, but that's okay. We're going to make it work. So I wanted to first introduce myself. I went to USC for my PhD. So I got my PhD at USC. I also did a postdoc there. PhD was in stroke recovery, specifically looking at NMDA receptors for glutamate. So if any of this is familiar, great. If it's not, no big deal. We can talk about it as it goes along, or if it even comes up. Then in my postdoc, I looked at oxytocin in essentially like an autism model, but it was really for our purposes more like a social bonding in rodents model. So we could talk about that if you're interested. I also have an 11th grader at CCUSD and a 7th grader at CCUSD, so I thought that might be of interest to you guys. And I don't know if you know, but I'm on the school board in CCUSD as well, so I spend all my time thinking about K-12 education. So I've been out of grad school for a while, and I'm teaching full-time at Antioch University. Those students are graduate students getting their master's in family therapy. They're going to be psychotherapists. I teach all the neurobio courses, and then I do consulting, kind of stuff like this, for also, additional work. So what I thought we would do is maybe start with plasticity and see if we can get some organic question and answering going from that. And if not, I can refer to the questions that you sent me in advance. And I was hoping, and I know some of you have been doing some of this studying on your own, and some have not been introduced to almost any of the neuroscience yet. But I was wondering if any of you would be willing to take the bold move of starting to talk to us about what plasticity is. Ooh, I already got a hand. That's great. I really can't move. Can I want to, because I would love to have you be on the mic, because I want to hear what you have to say. Maybe I can move this one.
Yeah, let's move it first.
So I forget who raised their hand.
Want to come up and talk
Yeah,
in the mic?
actually, why don't we do that?
Let's
That'll
do
be
that.
better.
Come on up.
That'll be better. Great.
We'll turn it like
And
this.
tell me your name. Zion?
Diane.
Diane. Okay.
Make you too nervous.
Okay. Is it the tendency of a brain or neuron to rebuild itself after damage?
Okay, great answer. The tendency of a brain or neuron to rebuild itself after damage. Anyone else? Any other contributions? And I can repeat what you say in the mic. What else? What is plasticity? Go ahead.
Does that have something to do with how parts of the brain can pick up the functions of other parts of the brain when it's
I can't carry it around.
Also about damage. I like that you guys are thinking about recovery. That's very important. It's totally what I studied for 6 years in grad school. Absolutely, it's a really important part of recovery. Let's put recovery to the side for a second. So we're not thinking a damaged or diseased brain. Just generally speaking, what do you know about plasticity? You could even think about the word plastic and what it means to you. Oh, go ahead.
I think in the context of education, isn't it the brain's tendency to change or grow? Like for instance, if you learn something new, your brain changes in some way. That's why it's called brain plasticity.
That's right. So right now, I'm totally changing your mind. I'm changing your brain. I'm having an impact on the neurons that are in your brain right now, because all learning is a product of plasticity. There's no learning that isn't from the experience that we have in our day-to-day. And in fact, there's a very specific recipe for how learning best happens. One of the questions that I got, and I'll use it as an opportunity to launch into this content, was how does the brain decide or what's the algorithm for how we have short-term memories versus long-term memories? It's a really important question. Short-term is like, I heard you guys talking about the permission slip for a field trip. I have to think about the permission slip for this field trip. It's due today. Oh my gosh, I missed the deadline. It's because I forgot. It slipped out of my short-term memory, right? But after you turn it in and after you go on the field trip, are you likely to remember the deadline for the permission slip that you did or didn't make? Probably not, right? It's probably going to be removed from your brain storage. But there are other things that are going to be retained in your brain storage. And I think it's important for us to think about like what the algorithm is. An algorithm isn't quite right. It's not exactly straightforward math in the brain, but there is kind of a general oversimplified algorithm for how the brain determines what is something I can forget and what is something I can retain in the long term. And the long term might be the field trip. Where are you going? Those of you who are going on the field trip? Okay, so virtual reality studio field trip. You might remember that for years to come because it might be so fun. What else might happen at the VR field trip that might allow you to remember it for years to come? Yes, so you might be very emotionally aroused either because you're amused or embarrassed or scared for them, right? So that's emotion. So I've named one of the pieces that is an important part of the algorithm for long-term memory, emotion, emotional salience. When do you do your best learning in the classroom? What? Someone say it loud. Yeah, when you're engaged, when you're really emotionally interested, you think it's meaningful for you. Okay, what else makes a big difference for retainment, long-term learning? Go ahead.
Well, I don't know if it's true, but maybe sleep.
Sure. Those are all really important. Go ahead. Yeah, practice is number 2. It's actually number 1. So practice is number 1 for long-term memory, for retaining something. Emotion is number 2. What's another one that you think factors into the algorithm for how the brain knows how to keep something from learning? And at this point now, we've defined plasticity as the changes in the brain that happen with learning. Okay, and then there was a question about what's the difference between short-term and long-term. So far we've said practice and emotion. What else? Failure is also really important, and it's embedded into the practice part. You have to have mistakes as part of the learning. In fact, I'm going to stop after the 2. So I've told you 2 of the variables in the algorithm. There are 4. So there are 2 more I'm going to ask you for before I leave today. That is, how does the brain decide what to keep? When does it do that, by the way? When you're sleeping. So at night, sleep is very important for these reasons. When you're sleeping, that is when the brain is reviewing the day's activities and saying all that short-term stuff, permission slip, what I wore, depending on who you are, right? All those things, they can go. But my trip to the VR studio, that was amazing. I'm going to remember it at least through the end of college or whatever it is, okay? But let's take a break and we'll come back to the other 4 pieces of the algorithm for keeping. I want a volunteer to come up here and do an activity, and maybe we can use it as a way to talk about this more. So who's going to come up? Come on up. Tell me your name. Talia. Okay, Talia's going to cut. So thank you so much for offering. I know it's not the easiest thing to do. You are going to look silly, but it's going to be totally fun, and everyone's going to support you. So what I'm going to have you do first is throw beanbags underhanded at that target. So just try to get it as centered as you can, and maybe I'll have one helper too. Exactly. Just do it a few times till you feel comfortable. Maybe walk forward 2 feet. There you go. Exactly. Just keep doing it till you get like 3 in a row. 1, 2. Oh, yeah. And then if someone could pick up, if I could have a student pick those up and bring them back, that'd be great. Okay, great. So now we're going to make it harder. I just had them. Oh, here they are. So we're going to put these on Talia. And I'm going to do it for you. I hope that's okay. Is that okay? Okay. So I'm going to put these on Talia, and then I'm just going to ask you to do the same exact thing. The instructions are the same, okay? Hold on. Okay. Now try again to do the same exact thing. Okay. And I'll keep handing them to you. Don't bend over and pick them up. Okay. So somebody say loud, what's happening to Talia? What's happening to her aim? She's. Ooh, good, good, good. Okay, so she just made an adjustment and got closer. Did you see her adjust? Oh. Okay, keep going. So we're going to try to get Talia to get 3 in a row. Guys, narrate what's happening. What's happening? So somebody said mistakes. Is Talia making a lot of mistakes? Yeah. And what else is she doing? So she's changing her behavior. She's iterating based on. There you go. 1, 2. Oh my God. Okay, wait. That was too fast. You're going to have to do a few more. You did really well, but I need you to do a few more just so we can make sure this works. Okay, so she's making lots of mistakes. She's adapting her behavior based on what? What information is she getting to let her change her decisions and her motor function? What? Yeah, she's getting like visual input, right? Her eyes are, she's hearing audio feedback. She's got motor feedback from what's happening in her. So just keep doing, I'll just make you do it a few more, because you already met the goal, but I want you to do it a few more times so we make sure it works. Just do these last 2 and then don't take them off though. Okay, so pretty reliable. Okay, now stay there. So now everybody watch, because we're going to take them off. And the second I take them off, I'm going to have you do it again right away. The same way you were doing it. Okay? Ready? 1, 2, 3, go. Right away. Go, go, go. Okay. So now what's happening? So what's happening? Do you have your driver's license? Do you have your driver's license? No. Okay. So we don't have to worry about that. No problem. Keep going. Keep going. Okay. So what's happening? You're switching hands on me? Yeah, you're to make sure you do it till you're back to normal with the hand you were using. Oh, wow. Are you sure you should be walking? No, go ahead. Okay. It feels good? Yeah. Does it feel 100% normal?
It feels kind of weird.
Okay. So do it until it feels like straight, like it's back. Oh, see, it's still off to the right a little. Yeah. It's going to take, about the same amount of time that it took to adapt in the first place. Okay. And you moved your body a little bit. But you feel okay? If you feel okay, we're okay. Okay. Great. So let's give Talia a round of applause. You can go back. Okay. So I would like you guys to kind of talk me through what happened. And also then I want you to answer the question about whether Talia will remember that later in life. Like long-term memory. Like tell that story to her children. So go ahead. Were you going to describe what was happening? You were not raising your hand? Okay. Can someone, or Talia, why don't you talk to us a little bit about how it felt too? Yeah. Okay. So if I can put you on the spot, how old are you? Okay. So Talia's been around for 15 years, and I'm assuming you've never put on goggles like that before, right? And so Talia has been used to visual information processed by her brain. What part of the brain processes visual information? Not the cerebellum. What part of the... All the way in the back, occipital lobe. Occipital lobe, way at the back, processes vision. So she's been receiving input that is where it's expected to be most or all of her life, right? So if it looks like it's in front of me, it is in front of me. I'm going to respond accordingly. But I just gave her glasses that are actually for teaching kids what being inebriated while driving is like. That's what it's for. They're called fatal vision. But they skew your vision by 30 degrees to the left. Okay? And so and you guys can try them and all that, and you look through them, and all of a sudden, what you think is in front of you is not in front of you anymore because it skews your vision. And how long did it take her to adjust? I mean, in the scheme of things, she did it all within the time period that was in front of us. Within about 5 minutes, she was able to adjust. And what was happening that whole time? Trial and error, absolutely. Lots and lots and lots of mistakes. And iterating, right? So like, it's the quantity of effort and practice combined with this iteration. She's getting lots of feedback from the world around her, visual feedback, auditory feedback. She's got some movement response that she's feeling from moving her arm. She can hear that it misses, et cetera, right? And then with time, with practice, she learns it. Even though she's had 15 years of experience up to this point of learning that everything is reliably in front of me if I think it's in front of me, she only puts these on for 5 minutes, and she's able to completely. What do you think would happen if she wore them for 2 weeks, 3 weeks? Yeah, she'd be able to drive. Or you guys aren't driving yet, many of you. So she'd be able to pack her backpack. She'd be able to make the tea in the morning, whatever it is that's happening, right? She'd be able to figure it out. And then if she took them off after 3 weeks, what would happen? How long would it take to learn how to be regular again after 3 weeks of wearing those? It would take a lot longer than it just took today, right? I wouldn't be able to send her off today to be fine. But those 5 minutes, so all of that is what? What did we just witness happening? That's plasticity, but is it short-term or long-term? Okay, so the learning of skewed vision by 30 degrees is short-term because she already took them off and we saw her get back her regular throwing, right? Now, will she remember today when she's older? Maybe, right? Because she stood up in front of 20 of y'all, 25 of you, your peers. So this actually gets me to the third variable in the algorithm for how the brain decides what to keep. What else is really important besides emotions and practice? Why is Talia likely to remember today when she's older? Yeah, and I would call that the practice because it's immersive. I think that's what I'm hearing you say, is you can't learn something by only reading it and understanding it theoretically. You do our mastery. When we become masters in anything, it's because we are immersed. We practice it. That's the practice piece. But what was I getting at with respect to Talia being up in front of this room in particular? Yeah, so the social input really matters, especially at this age, but it's important for all of us. We are fundamentally wired to be social. Hopefully some of you are going to be reading the content around mirror networks. Anyone read any of that yet? A lot of the learning that we do is just by observing others. And there are entire networks of the brain that fire as we observe others do things as if we're doing them ourselves. So while you guys were watching Talia throw this, there were networks in your brain, the same ones that make your right arm throw a beanbag underhanded, were firing. And what happens when neurons fire together? Do you know that phrase yet? It's like the most important one for plasticity. When neurons fire together, they wire together. Because which of the 4 variables in the algorithm is that? It's practice. So far we've got practice, we've got emotions, we've got the socially wired brain. We learn by observing others, but we also learn from the reward that we get from being in the presence of our peers. Which neurotransmitter is most responsible for reward? Dopamine. What else do we think of as dopamine being for? Happiness. Yeah. Joy. It's telling us, oh, it's good for your survival. Do it again. Socialization is very good for your survival. So you're very rewarded for socializing. So that's the third. What's the final and fourth variable in the algorithm for how the brain decides to keep it for long-term memory. It's not, I don't know that you'll be able to guess it, but we'll just give it a second. Do you learn best when things are really easy? Not usually. When do you learn best, do you think? Yeah, it has to be optimally challenging. In fact, you have to be equally as likely to succeed as you are to fail. It has to be 50% as possible for you to get the answer correct, and 50% as possible for you to get the answer wrong. So those are the 4 things that are required for the ideal learning environment, meaning that your brain is going to grow dendrites, add on tissue to the existing networks to make permanent, or it's never really permanent, but more permanent changes in the brain that allow us to have learned the content. Okay? So I wanted to start with a little opener of plasticity, but I also just wanted to answer questions. So I can start by going through the questions that you sent me, but I also want to make sure, do you guys feel like that stuff that I just introduced was clear? Okay, so tell me again, how does the brain decide what to put into long-term memory? Why don't you tell me? Practice, emotion, social, and challenge. Those are the 4 things, right? And so when things are difficult, we do not run from them. We embrace them. Okay, I want to share screen, but maybe I'll go to the questions right now. Do you want to ask me a question off the cuff, or should I go to the list you sent? You sent incredible questions. I love them. One of my favorite ones is, my friend is seriously trying to detoxify dopamine. Totally good question. What does it mean? My friend is seriously trying to detoxify dopamine. What does that mean? I'm happy to answer the question. Go ahead. I mean, in a lab, we could maybe do that, but could a person do that to their own brain? That might be dangerous. Yeah? Okay. Excess dopamine stimulus in our modern society. And you were going to say something? Same thing. What's the excess dopamine stimulus? What does that mean? Of what? Same. What does it mean? Okay. Okay. So I think what we're talking about is like particular kinds of feedback that we get from some of the screen time that we're using, right? And right now I'm hearing TikTok be named in particular. Okay. So that means that you all have some idea that TikTok is very rewarding in your brain, and that you've read somewhere or other, or somebody told you somewhere or other, that you get a big flood of dopamine in your brain when you're getting that feedback from TikTok, either engagement on your posts or because you're seeing other people's posts, whatever it is, okay? So that means you have some understanding of that. But again, we talked about dopamine briefly before. What is it there for? What's its job? If it's rewarding you, why? Why do we need to be rewarded? Why does the brain need to be rewarded? Like what? What do we need to survive? Eating. Well, yeah. Yeah. We need to eat, we need to drink, we need to procreate, we need to do all sorts of things that enhance our chances of survival. And the actual reality of that is that all of these things, like I also need to not trip and fall and break my head open. I also need to maximize, my social contacts so that I can better thrive in society. I could go on and on and on, right? We need a system in the brain that says this enhances your chance of passing on your genetic material to your progeny, and so therefore I want you to do it again. And I'm sure you know that people have addictions, right, to all sorts of things, but let's use drugs for right now, like recreational drugs, not prescribed drugs. So when people have addictions to illicit drugs, like illegal drugs, why is that happening from a brain perspective? Yeah, almost entirely. I'm just going to make one addition. So we have a system that is there to say, do it again, it's good for your survival. That's its whole purpose. By the way, dopamine is important for a bunch of other stuff too, like your motor function really depends on dopamine. That's why when people have Parkinson's, they lose a lot of dopamine producing neurons and their motor skills decline and they begin to get shaky and they have a loss of motor control. So I don't want you to think dopamine is only love and reward and all those things. It's very important for lots and lots and lots of stuff, especially motor function. But in terms of this question of like a lighter question of TikTok, but maybe a more serious question of addiction, is that we have a system, its whole purpose is to say, this is good for your survival, do it again. And most or all drugs of abuse, what neurotransmitter gets released in the brain when you do them? Dopamine. So now the brain is actually saying to you, this is good for your survival, do it again. If dopamine is released when you're using TikTok, that means that your brain is getting an actual message that says this is good for your survival, do it again. So when we say detox, it's not that, and I wanted to add that it's actually not that the receptors go up, it's that they go down. So the body has a constant, this you must know from bio, right? We have a constant effort at trying to maintain homeostasis. Yeah, what's homeostasis? Say it. Regulating, like you have to get back to baseline. Like you have a different body temperature in the morning than in the middle of the day and then at night, right? Or you have a different water intake, or you have different levels of cortisol, which is like it helps you wake up, but it can also be a stress hormone, etc. Homeostasis is the body constantly trying to get back to its baseline. Always, always, always. So if there's a bunch of dopamine in the brain that it's not used to, it's going to actually down-regulate receptors. What are receptors? Yeah. Yeah. Do you guys know what a neuron looks like yet? So I want to share a picture of a neuron so we can at least look at the, but I'm really struggling because it's a PC. And you know how Mac people and PC people like don't get along. So I wouldn't mind some help right now because I want to share slides. I just want to put a picture of a neuron up. That's all. We don't need to do a whole fancy thing. Those are the slides. I'm fine on a Mac. I can't. Oh, okay. Okay. Well, you can picture a cell, a regular cell, not a neuron, right? It's like a circle or a sphere. If you can picture, if you've ever seen a picture of a neuron, it doesn't look like a circle or a sphere, right? What does it look like? Yeah, it's like got a big old like head area, the cell body, and that has huge branches coming off of it. Those are called dendrites, right? Then it's got a really long what? Axon. That axon often has what around it? Myelin is often around the axon, which helps the signal transmission. We could spend a long time talking about myelin too. It's really important. It's made up of fat. Fat's really important for your brain. And then there's projections all the way at the end. And so it looks like a thing out of Dr. Seuss or something. I mean, it looks really wild, bizarre, like, you know, something that doesn't live on the planet Earth. And all around it, all around the entire thing are these receptors that are inserted into the membrane. So I think that you've probably learned about a membrane, phospholipid bilayer that surrounds the entire neuron. And then there's stuff shoved in there. Right? And receptors are one of the stuff. And receptors are there to receive information from outside the cell. So again, back to dopamine, if the brain is getting floods and floods of dopamine, it's probably going to say it's too much. I'm making less receptors. So actually what happens when people do illicit drugs, the way they get tolerance, which is what you were describing, is because the brain stops making receptors for dopamine. So when people recover from a heroin addiction, they often have what's called anhedonia, which is a lack of joy, because they've now got almost no dopamine receptors, so they cannot experience their natural sources of joy. Pretty intense. Okay, so I don't want to waste any time because we do not have infinite time. So I'm going to just run through the questions that you sent me, but also just raise your hand if you have questions, because otherwise I'll just go on about what I want to talk about. You know what I mean? So the detoxified dopamine one, I mean, yeah, I think it's really good to take some time away from our screens, but it's not because I'm concerned about dopamine. It's because I'm concerned about our attentional networks. Have you guys read anything about our attentional networks? Maybe we could talk about that for a second. Do you know that we have 2 different attentional networks? One is external, like you're using it right now, paying attention to me, and one is internal. And you only ever use your internal attentional network when you are not attending to stimuli in the outside world. Okay, so you would actually have to be lost in your thoughts, which it turns out is really important. Daydreaming is good. I mean that. Or if you're on a long drive and you tune out, or in the shower, like when do you have aha moments? So it's like you realize why your friend got mad at you all of a sudden, or maybe something academic where you like figure out what you want to do. When do those moments happen? Do they happen when you're like on deadline for a paper? When do they happen? When you're relaxed, sometimes right when you wake up, sometimes right when you're falling asleep, in the shower, driving, maybe exercising, when you're lost in your thoughts. Those times when you are ignoring the external world, we almost never do that. We do not have a society that really kind of curates time for that nothingness. We're all really externally driven, myself included, so it's not a judgment thing. That's the only reason I would care about detoxifying, is not so much because of dopamine, but because we are so tuned in externally, we are underutilizing an entire attentional network that's really important for deep cognition, for creativity, and empathy. We understand now in neuroscience that all those really important things depend on that internal attentional network. If you want to look it up, it's called the default mode network. Okay? So another good question was, is there an equal amount of gray matter and white matter? What's gray matter? Go ahead. I saw your hand. Yeah, it's cell bodies. It's the part of the neuron, and we kind of walked through the neuron. So for those of you who are yet to be introduced to the neuron, hopefully this will come back when you're looking at the pictures in the book and so on and so forth. But when you picture that neuron, it's got the cell body, it's got dendrites off the top, it's got the long axon, and we talked about the long axon that is covered sometimes, a lot of the time, in myelin, which is fat, right? And so what color is fat? Yeah, a lot of people say yellow, but let's just think of it as white. So when we're talking about white matter and gray matter, all we're talking about is the axons that are covered in myelin are white. And so that's the signal traveling either across the brain, very often across the brain, but also to other regions of the brain. And the gray matter is just cell bodies that don't have myelin coating them. Okay, so great. And by the way, there probably is more white matter because there's just a lot of distance to travel in the brain from a neuronal geographical standpoint. But I don't know that we know that down to the perfect measurement, but I think there's more white matter than gray matter. Guys, raise your hands if you have questions. Yeah, go ahead. Optogenetics, and then what's the question? I'm not an expert on optogenetics. I saw a lot of questions about myopia and monocular deprivation and stuff like that. Those experiments are very seminal in neuroscience. They were really important. But they're essentially just plasticity studies. It's really just about, it's how we first learned that we have critical windows of development, right? And so that after a certain age, if you have not gotten enough visual input, you will not have fully functional vision. Same thing with some of these very basic things like hearing. Some language stuff is dependent on early phases of learning. There are social windows of development. This is it right now. I could go on. We do have critical windows of development. That's how we learned that, is from those experiments where they deprived owls of one of their eyes of input. They would put a patch over their eye and see, well, now that they're 2 years old or whatever, if we take the patch off, can they get normal vision? They cannot, and so on and so forth. But you had a question? Awesome. Yeah. Sure. I don't, go ahead. Okay, Jose. So Jose, try to figure out your mute, but I'll keep going until you do. Okay? So another question is what's I'll get to you in a sec. I'll just go with this one. What's norepinephrine? Any of you know that? It's another neurotransmitter. Dopamine's one, serotonin's another, norepinephrine is another. But you guys, some of you must have EpiPens or have siblings who have EpiPens. It is the same as what adrenaline does. So epinephrine is what's in an EpiPen, and it is adrenaline. That's all it is. It's adrenaline. It's the thing that's going to get your fight or flight system in the up mode, in the I have to fight mode, and it's just called NOR for NOR is brain, and epinephrine is just what we call it when we're in that scientific medical field. Did you have a question? Yeah, I mean, are you interested in like the experience of being in research? Because I did see that question. Or are you interested in like the details of the thesis? Yeah. So in grad school, it was stroke recovery, which was so interesting to hear you all talk about plasticity from a recovery standpoint right in the beginning. So I hope it's okay. I'm just going to like tell the whole thing, which includes working with animals. And that is often a big part of graduate school if you're in the research world, in the medical field, or anything biology. And so I was working with rodents and most of the time with rats, and rats are very much like humans. They have the exact same neuronal structure. They have very similar anatomy, except that they're missing a really important part of the brain that we have that's very uniquely human. What part of the brain is super uniquely human? No other species has it like us. Yeah. Yeah. Every single species with a brain has a brain stem. Rats do also have a cerebral cortex, but it is part of the cerebral cortex. It's here. It's the prefrontal cortex. It's called the PFC. The CEO of the brain. That's very uniquely human. So rats, awesome. Jose, I'm going to get to you in 1 second. I was going to tell the studies. So rats have neurons just like we do and have very similar anatomy of the brain, right? They have like a frontal lobe and a temporal lobe and an occipital lobe and a parietal lobe. And so I would give them a lesion. It was equivalent to a stroke. So I'd go in there and do a little bit of damage in their brain. Then I'd give them some immediate post-stroke recovery time. And then, because I did the stroke on one side of the brain, it affected what side of the body? The opposite side of the body. So I'd lesion the left side in the motor cortex, and then they'd have an inability to use their right paw to reach and grab a pellet. And then I would try to help recovery. And so I would, it was through glutamate receptors. Glutamate is also a neurotransmitter. Glutamate is the most, it's like the oldest, the simplest, maybe you could call it the most important neurotransmitter. It's everywhere, it's for everything. It's always excitatory. So you'll learn about excitatory neurotransmitters versus inhibitory neurotransmitters. Glutamate is always excitatory. It's always going to make neurons fire. And when neurons fire together, they wire together. And so I would just try to change the glutamate receptors so that they would recover more quickly. Beyond that, it's probably too complicated. Jose?
Hello? Can you hear me?
Yes, we can.
Oh, hello, I'm Kevin. I'm a student from Alhambra High, and during the action potential, the charge goes below resting, right? How does the charge go back to resting? In the packet, it says because of the sodium-potassium pump, but I don't quite understand how that works.
Yeah. Yes. So what we're talking about is neurons firing. So neurons that fire together, wire together. And the technical term for what we call in layman's term firing is an action potential. And by the way, can you have like a baby action potential or a little action potential or a part action potential? It's all or nothing. So action potentials are all or nothing, which is why computer modeling is so important in neuroscience, because it's ones and zeros. So you either fire or don't. You are never just a little bit pregnant. You're either pregnant or not. So it's a 1 or a 0. So action potentials fire or not. And so the reason that that happens is technical and fascinating and YouTubeable, and I invite you to take a look. But the question is, when an action potential happens, the neuron is at a particular voltage at rest, and the signaling in our brain is composed of two different kinds of signals. What are they? More generally, not the specific ions, but what kind of signaling is in the brain? And electrical and chemical. So electrochemical signaling in the brain. And so within a neuron, it's what kind? Electrical. Then between neurons, it's, right, that's where the neurotransmitters are, is in between the neurons. There's a space there called a synapse. Okay, so but the action potential within the neuron happens because there's stimuli. Maybe I kicked you in the toe and you got some input, some pressure input, and it led to a voltage change. And again, all that is complicated. It's a little hard to suspend belief and just go with what I'm saying right now, but just go with it. There's a voltage change, and the neuron was at rest, and all of a sudden it becomes less at rest, and we call it depolarization. So actually, it rests at negative 70 millivolts. That's an accident. It rests at negative 70 millivolts, and then all of a sudden there's stimulation that makes that voltage go up. So it depolarizes from negative 70, passes 0, then goes all the way up to positive 50, then comes all the way back down to negative 90, so it passes its resting place. This is the whole course of an action potential. You will see this in your book and elsewhere. And then when it comes back down, it's like, it's called hyperpolarization, as in like it's gone too far. And that is a really important period where there's like a buffer, so it cannot be stimulated to have another action potential again during that time. And then it comes back to rest again. All of this phase, this action potential phase, is dictated by channels that are voltage gated. They're very sensitive to a bunch of different criterias. But then when it gets to that hyperpolarized stage, and I hope I answer your question now, Jose, that is when the sodium-potassium pump gets it back to its resting potential. And I don't know if that's actually what you really wanted to know, or if you're really interested in the voltage gating part, that is the depolarization and repolarization. But the sodium-potassium pump is helpful when it's hyperpolarized and it gets back from negative 90 to negative 70. Did that answer?
I thought the sodium-potassium pump takes out 3 positive ions and puts back in 2, which would indicate that it makes the cell more negative. Wouldn't that, I just thought that didn't make much sense.
Got it.
Yeah.
Yeah. So there are lots of really big, bulky, positively charged positively charged particles inside the cell called anions. Have you read that part? It's a complicated answer, Jose. So we need to maybe talk offline about it. But the inside of the cell has a bunch of things that keep it at its stable resting potential that is not just about the pump, but is partly the pump. Okay. So I think does it mean we're at time? Okay. I hope it was fun. I will see you guys. I hope you do well. Thanks.